Okay, so we have a screen Coulomb potential, yeah, of a point charge Q. Um, and we're asked to find the electric field associated with this potential, yeah, and figure out the charge distribution that produces this potential. Okay, well, we know the relationship between electric field and potential. Once we know potential, if we take the gradient of that, except that we have to do it here in spherical coordinates because that's given in spherical coordinates. If we take the gradient of V, multiply that by minus sign or minus 1, we get the electric field. Okay, so I will start this part A here. E of R equal minus gradient of V. So this will be minus Q over 4 pi epsilon d over dr of e to the minus r over lambda over r. Okay, and so quotient rule here, so let me continue here, minus. So derivative of on top is minus 1 over lambda e minus r over lambda, this is with respect to r, times r, minus derivative of r is 1 times the numerator minus r over lambda all over r squared, and so this will be, I'm going to factor out e to the minus r lambda, and I will get and by the way, this is in the radial direction because this is the r component. There's no theta or phi component for this, so we will get if I pull out so this is going to be, they're all negative, so q e minus r over lambda over 4 pi epsilon, and I'm left here with 1 minus or plus lambda r, 1 over or r over lambda, and this is r hat over r squared. I pulled out r squared from this, so this here is my electric field. E of r. Okay, and find the charge distribution that produces this potential. Okay, we know that delta E, divergence of E, is equal to rho over epsilon. This is Gauss's law in differential form, or the electric field in differential form. Okay, so all I need to do is find the divergence, so that means rho would equal epsilon times the divergence of E. So all I have to do is find the divergence in spherical coordinates, and that is let me write it down. We don't have a theta component or a phi component, so the divergence would be 1 over r squared d over dr of r squared times the electric field. So times let me put 1 over r squared here, which is this, so I could cross it out. And then we have 1 plus r over lambda times e to the minus r over lambda, and the rest are constants, 4 over 4 pi epsilon. Okay, so I need to differentiate this term here with respect to r. Okay, so we're taking the partial derivative of this with respect to r. Okay, let me pull the constants out. So I know that this is gonna become q over 4 pi r squared. Okay, let's start differentiating now. So product rule. So we get 1 over lambda times right. Actually, 1 second, there's a slight modification here. There's a divergence of r over r squared. Let me try to write this in a different way because it will become a little bit confusing. Let me erase this. Yeah, let me erase all this. I'm just gonna write it in a slightly different way so I don't have to orally do the derivative of the divergence. I wanted to show you exactly where it falls into the expression. Okay, so rho is equal epsilon. Okay, now q over 4 pi epsilon is a constant, so I'm just gonna pull them out. Okay, and then I have e to the minus r over lambda times 1 plus r over lambda okay, 1 plus r over lambda times the divergence of r hat over r squared, which, as you remember, has a Dirac delta function in it because this blows up at the origin. So that's why I wanted to do this in a slightly different way so I could show you how I can take care of this step. So let me open this. Okay, plus, okay, now so I'm using the product rule here, so divergence, so this is going to be now r hat over r squared. Okay, so I use the product rule on the divergence so I can take care of the divergence of r over r squared separately. So r over r squared dotted with the divergence of e minus r over lambda times 1 plus r over lambda. Okay, now this guy here has a value from chapter 1 of 4 pi, so it's 4 pi at any point at the origin if you integrate using the divergence theorem, but then it blows up at the origin, so anywhere at 0 we engage the Dirac delta function to save this from blowing up, because it's 0 everywhere except at the origin it's 4 pi. So this Dirac delta function picks up the value at 0 and zeroes out everything else. Okay, and so now we get let me do this on the side here. Okay, I'm going to do this on the side. So this is the gradient of E minus R over lambda of 1 plus R over lambda, and this is going to be in the R direction. Okay, d over dr of E minus R over lambda 1 plus R over lambda, and this is going to be R hat. Here we have to engage the product rule. I may not have enough room here. Let me continue here. So this is equal to R hat minus 1 over lambda E minus R over lambda. So this is the product rule. 1 plus R over lambda plus, first as is, E minus R over lambda. Derivative of the second is 1 over lambda. Oops. Okay, so this will be, let's see, if we FOIL this, we're gonna get R hat. This is gonna be, these first two terms will cancel out, because when I multiply this by 1, it's negative the second term, and all I'm left with is minus R over lambda squared. Okay, R over lambda squared E to the minus R over lambda. Okay, so this is that last term there, and I know that when I let me actually take this down here. Okay, so I wanted to do this here. So now we have this term times 4 pi Dirac at R. Okay, and so what that will be, let me write it on the side. So E minus R over lambda 1 plus R over lambda Dirac, or 4 pi now. So I'll replace this with 4 pi. Okay, so what a Dirac delta function is, it tells you that anywhere where R is not 0, this whole thing is 0, except when R is 0, this the function that sits next to the Dirac takes the value at R equals 0. So I will evaluate this at R equals 0. So I get e to the 0 times 1 plus 0 times 4 pi, which will, as you can see, will just be 4 pi. Right. Which we could write it as cube Dirac delta function at R, because that's what that is. Okay, so now plugging all this in, so back to rho. So rho equal epsilon canceled out, we get q over 4 pi. Okay, this whole first term now is 4 pi the second term turned out to be r over r squared right, or plus r over r squared times that turned out to be, well, it's a dot product between r and r, so I could eliminate this r since it's 1, and I have minus r over lambda squared, so there's lambda squared here, e to the minus r over lambda, right? And so I could cancel an r with an r, and I get rho to be q over 4 pi times 4 pi Dirac delta function at r minus 1 over r lambda squared e minus r over lambda. This is my rho. And sketch it. You could do this on the computer or whatever. I'll skip that part. Show by explicit calculation over rho r that the net charge represented by this distribution is 0. Okay, well, that means we have to integrate this over d tau, because q is rho d tau over the volume. Okay, so this would be let's continue here, q over 4 pi integral of we have 4 pi Dirac d tau on v minus 1 over lambda squared. We have e minus r over lambda over r, so this is over r, then d tau is r squared times sine theta dr d theta d phi, so this is a triple integral, right? And r is going from 0 to infinity, since we are integrating the entire charge. This is a sphere 0 to pi, and this is 0 to 2 pi. Okay, we know that this is 1, right? That's the definition of the Dirac delta function. So when you integrate it on a sphere, it picks up the value of the function next to it, which is nothing, 1, evaluated at r equals 0, but 1 is a fixed number, so at r equals 0 it remains a 1. So we get 4 pi into 1, or 4 pi, because we have 4 pi outside the integral, okay, minus okay, so 1 over lambda squared, the r cancels here, and I get r e minus r over lambda dr. This is from 0 to infinity. We have 0 to theta, 0 to pi on sine theta d theta, and we have 0 to 2 pi on d phi. Now this guy will be 2, this guy will be 2 pi. Let's check out what this guy is. I'm gonna do this on the side.
It's not that much more. I factored out the e.
this is going to be integration by parts. Okay, and integration by parts, I'm going to use the tabular method here, it's just quicker. So I'm evaluating now on the side RE minus R over lambda dr. Okay, from 0 to infinity. Okay, so this is going to require integration by parts. I'm going to use the tabular method. E minus R over lambda. Derivative of R is 1. Derivative of 1 is 0. Integral of this is itself divided by the chain rule, which is minus 1 over lambda. So I would multiply it by minus lambda, and then if I integrate it one more time, it's the same, except now it multiplies by lambda, so minus lambda, so it becomes lambda squared. Okay, and so this times this minus this times this, and everything else will be 0 because this is 0. So that means the answer to this one is going to be minus R lambda E minus R over lambda minus lambda squared E minus R over lambda, and we are evaluating this from 0 to infinity. Now notice I could factor out E minus R lambda, so I would get minus R lambda minus lambda squared over E to the R over lambda from 0 to infinity. Now infinity, I'm going to get minus infinity over infinity, so I'm going to use L'Hopital's rule here for the infinity bound. For the 0 bound, it's simple, I know what the answer is, but for the infinity bound, I'm going to use L'Hopital's rule. So this is going to be minus, so I'm going to take the derivative on the top with respect to lambda, with respect to R, so minus lambda, second term is 0, over the derivative of this is 1 over lambda E to the R over lambda, and then I will evaluate here as R goes to infinity. Okay, now now I'm going to evaluate the lower bound, the 0 bound. So 0, I get the first term is 0 and the second term is minus lambda squared. Okay, now as R goes to infinity, I get, notice, I get minus lambda over infinity, which is 0. So this whole term goes away, and I have left minus lambda squared. I get lambda squared. So the answer to this guy, lambda squared. So then I go back to Q now. So Q is equal to Q over 4 pi, okay, 4 pi minus 1 over lambda squared and then this integral R E minus R over lambda turned out to be lambda squared, and then I have a 2 for sine theta d theta and 2 pi, so that's 4 pi. So that's okay, so I have 2 times 2 pi is 4 pi. Notice these cancel and I get exactly 0. 4 pi minus 4 pi is 0, so Q equals 0. Okay, so so that confirms by explicit calculation that the rho r, if we integrate over rho r, the net charge represented by this distribution is 0. Okay, Yeah,